Uh, this is the homework 3 of the Generative AI course. So, the homework assignment requires us to give a prompt to ChatGPT or whatever LLM and to generate a Colab notebook based on the prompt. So first, I submitted this prompt in the following to ChatGPT, and based on the response from ChatGPT, I generated the following notebook concerning how to understand the Softmax functions. So this is the content. You can see it. We first introduced the concept of Softmax and the mathematical foundation, basically the definition, and a really short implementation from scratch, and some interactive explorations. And we want to discuss the winner-takes-all effect and the sensitivity to perturbation, the temperature parameters, and some real-world applications, and final result summary. So, as introduced during the lectures, softmax is just a mathematical functions that converts a vector of real numbers into probability distributions. So it is widely used in multi-class classification, neural network output layers, and attentional mechanism. And of course, reinforcement learning also uses softmax. So why it is called softmax? So unlike the hardmax function that output 1 for the maximum value and 0 for others, softmax provides a soft probabilistic interpretation where the maximum value gets the highest probability, but other values still retain some probability. So mathematical foundation is just a definition. It's exponential to the input value and normalized by the sum of other exponential values. So the output range is between 0 and 1, and it is a probability distribution because all the sums to exactly 1. Okay. So the implementations are relatively simple. So you can just see the code here. Yeah. So let's say we input 3, 1, and -2. So we just convert it to according to the function here. We will get the final output here. So we can see that the probability for class 3 is really relatively small. So this explains the winners. This serves as an initial demonstration about the winner-takes-all effect. You can see that class 3, the smallest one, get almost 0 probability distribution, while the largest one get almost 1 probability in this distribution. So we can do some interactive. You can change the input function here, the input value for the 3 class here, and to see the final softmax probability. And only thing you need to be careful that you only need to see the yellow one here, softmax probabilities. The normalized scores is we just use the min-max normalize. Basically, you just using your current scores minus the minus scores among the 3 class and divided by the maximum score minus the minimum score. So this is called the min-max normalization. Okay, you can just adjust the bar here to see different results. Yeah, and also here Okay, this is the same. So the winner takes all effect, as we introduced before. But for all equal, there's no winner takes all because everyone is equal. Okay, so for small differences like point, this example is input is 1.1, 1.0, and 0.9. You can see that the winner takes all is not so significant for small differences. For medium differences, for 2, 1, 0, we can see a lot slightly. For example, in the original percentage, 2 is consists of 2 out of the third, right? So the min-max quite proportionately reflects the original distribution. But you can see that in the middle one, originally is 1/3, but it decreases a little bit to 2/4, and why it decreased because the third one originally was 0, but after exponential it gains some probability distributions. So you can also see the softmax function as a redistribution of the probability. But for large differences like 5, 1, or -2, you can see the winner takes all function is really significant for large differences. Although originally 1 consists of, if you does not consider the -2, it consists of 1/5, but after the softmax, it only consists of 0.2%. So you can see that for large differences between the 3 classes input, we will have a really significant winner takes all effect. Not to say very large differences, and this is exactly winner takes all. And of course, you can observe this effect by yourself here. We also provide the interactive interface overview. And sensitivity analysis is we want to determine whether some perturbation will affect the final outcome. For this example, like here, for the original one is 2, input is 2, 1.5 and 1. So if we perturb, we add a 0.5 probability to class 2, then we will have 2, 2, and 1. But you can see that the final probability, the final ranking is totally different. So, but this is a specific case, but in general, really based on your the relative magnitude between classes, that will determine whether the softmax outcome is sensitive or not to the input. But for most cases, we will normalize the input before feeding them into the softmax functions. So a lot of times we will have, after normalization, we will have relatively small differences, so the winner takes all effect is not so significant. So the sensitivity, in terms of sensitivity, maybe it will be relatively significant, because if you add some perturbation to relatively small differences, the input will flip, right? Okay. Also, we consider an modified form of the softmax. We add a so-called temperature parameter to the function here. If you see here, where is the temperature? Let's see. Sorry. Let's see the temperature. This is the argument, right? Explore temperature. So softmax with temperature, we okay, here. So basically, softmax with temperature is at the upfront. We just divide all the input array to a certain temperature and feed the kind of normalized inputs to the softmax, and we will see what's the effect of the so-called temperature to the softmax distribution. So I can just see this graph. So for temperature smaller than like 0.1, the so-called winner takes all effect is relatively significant. For if t equals to 1 is the original softmax, right here. So the winner takes all is not so significant. So if you want to mitigate, you want to ameliorate the effect of winner takes all, you can just increase the temperature so the distribution will become more not so sharp. It can become more smooth, like the yellow one here, if we set the temperature to 5. Okay, this is a comparison. So for small temperature, winner takes all. For large temperature, almost everyone get a relatively equal, relatively comparable value. And in real-world application, as we mentioned in the introduction, there we can use in the, for example, the word prediction. In LLM, there's a lot of variation, but basically is the most likely probability, the highest probability for next token probability. See the details. I'm not going to scrutinize every details here. And attention mechanisms, yeah, there's also in the transformer and also in some RL applications, but we are not going to see every details. So summarize, we can see that the softmax do have some so-called winner takes all effect for large input differences here, but for small differences, we do not see the effects so drastically. And also we can see that the temperature do have if you have a relatively large difference between your inputs, you can whether normalize it, or you can just modify the temperature parameter to a larger scale to mitigate the winner takes all effect. And that's all. In the end, we do the ChatGPT do provide the so-called quizzes. If you're interested, it is in the end of the of this notebook, and that's it. So we can see this is a final graph to summarize all the points that we mentioned today. And thank you for your attention. And that's my homework 3.